So, welcome to this class on hardware security. So, we shall be continuing our discussion on fault tolerance with respect to cryptographic implementations. So, we shall be starting to discuss with where from we left last class, that is robust codes for AES. We shall be talking about time redundancy countermeasures and also bias fault attacks and eventually on differential fault intensity attacks. So, to start with, we have already kind of seen how to apply like parity for in the context of AES, and as we discussed, right, parity never gives us like like 100% coverage. In fact, right, it is very difficult to develop codes which gives 100% coverage, but the thing is, right, there is a quite significant portion, right, in linear codes, or there is a significant population of faults which are missed in such kind of parity based detections. Right. For example, if you are just checking for even parity, you know that like if there is like for example 2-bit faults, for example, you can never catch them because the parity, right, if in case of 2 flips will remain the same, it won't change, and therefore, right, it can get bypassed. So, therefore, right, there was an alternative strategy which was published in a paper in Dependable Systems and Networks in 2004, and there are some following works also which basically tries to develop what are called as nonlinear codes in the context to such kind of protections. Okay. So, I will just try to give kind of a very brief overview on how it works. So, let us see, right, how we can kind of for example adapt it. So, we know that like when we talk about linear codes, we basically very briefly, right, has got, so we have got a binary linear n comma k code, for example. So, this is a binary linear n comma k code with say 2k which is greater than equal to n. So, these are like useful constructs which are used in the context of linear codes, and we have got like what is called as a check matrix. Okay, and this is a very usual matrix which is used, and this has got two components. One is a p of n minus k cross k, and that is followed by an identity matrix which has got a dimension of I n minus k cross n minus k. Okay. And this is usually defined over GF2, that means the elements here are binary elements. Okay. So, this you can easily understand will have got a dimension of n minus k cross n. Okay. So, now if you take this matrix, the idea is that you essentially can define a corresponding matrix which is called as the generator matrix, which is essentially denoted as in this way, that is, suppose this is I k cross k, and that is followed by say p n minus k cross k. Okay. So, this totally will have dimension of n cross k. Okay. So, you can easily verify that if I do h into g, like if I multiply h into g, then I will get this as kind of, you can write this as p concatenated with I multiplied with I and followed by p. So, this is basically p plus p. So, therefore, this is equal to 0. Okay. And so, what we do is that suppose there is a message m, and we basically kind of transform this message into a corresponding code word for the message by like applying your generator matrix G and basically getting GM, for example. Okay. So, now you can basically see that what we do is that we basically kind of compute what is called as a syndrome on the code word by taking this GM and applying the H matrix on it, that is applying the check matrix on it. Now, since H of G is equal to 0, I get the syndrome as 0. Okay. On the other hand, if right there is an error, if because of an error, what happens is that this code word gets kind of polluted to something like C plus some error E. Okay. Then when you apply the check matrix on C tilde, you get H of like you basically have C plus E, and as we know that H of C will be equal to 0, we get what is called as H of G, and this is essentially a non-zero term. Okay. And that kind of alarms us that there is an error. Okay. So, now the question is, right, and without going into details, because this is a like subject in itself, we know that like the number of undetectable faults or like undetectable errors is equal to 2 power of k. Okay. And the number of detectable errors, okay, that is detectable errors actually like interestingly with probability 1, because for sure they can be detected. We have got something like the remaining thing, that is 2 to the power of n minus 2 to the power of k. Okay, that is all of them would be detected, but at the same time, right, there are 2 to the power of k errors which are not detectable. Okay. So, then here we like bring in the concept of what is called as nonlinear codes. So, this is an example of, this was an example of linear codes. Okay. So, in nonlinear codes, you basically try to kind of like increase the or rather decrease the number of undetectable errors, albeit, right, you basically kind of like for the remaining errors which you can detect, you can afford some amount of probability of missing them. Okay. So, the idea is that here you basically take the, so that the linear code, for example, the linear code, okay, V is converted to a nonlinear code, okay, to nonlinear code. Again, I denote it as n comma k and write that as CV. Okay. So, I will give an example which we often use in the context of cryptography, and so this example essentially is, or in the context of fault tolerance for cryptography, is based, so it is, let me denote it as CV, where CV is nothing but x comma w, okay, where x suppose belongs to GF 2 to the power of k. So, that is, for example, in AES it is GF 2 power of 8, and then I calculate this w by applying a matrix transformation denoted as P, okay, on x, and then performing a finite field cube. Okay. So, this essentially belongs to GF 2 to the power of r. So, there is kind of a compression and then followed by like converting this into GF 2 to the power of r. So, clearly you can see that which kind of errors will basically get missed. Okay. So, if you observe that, so that would mean that if there is an error, so consider there is an error, okay, and this error is denoted as say Ex and EW. Okay. So, that would mean that suppose I have got x and w here, I basically make an error in x and I make an error in EW, such that this resulted term also falls in this code word. Okay. Then it cannot be detected. Okay. So, for example, what will happen here is that this will become x plus Ex and this will become w plus EW. Okay. And that means that now the code word for x plus Ex will be P applied on x plus Ex, okay, and then I do an whole cube on that, and that should be equal to w, right, plus EW. That means like w plus EW. If that happens, right, then it cannot be detected, because this is the corresponding code word for it, because then this also becomes a valid code word, and therefore, this also belongs to CV. Okay. And what is w? W is nothing but Px whole cube plus EW. Okay. So, if you basically make an analysis of this equation and see like how many are possible solutions, and which essentially can if any solution for this will be missed. So, therefore, the error which essentially kind of satisfies this equation will be missed by this code word, will be missed by this code word. Okay. So, therefore, right, if I just summarize the result, here we will see that the number of undetectable faults, right. So, remember, right, in the previous case, right, it was so in this case, right, it is 2 to the power of k minus r, okay, and the number of errors which are detectable with probability of 1 is equal to 2 to the power of n minus 1 minus or plus 2 to the power of k minus 1 minus 2 to the power of k minus r. Okay. And the number of, so interestingly, right, you will have number of some errors or number of errors which can be detectable with a probability of 1 minus 2 to the power of minus r plus 1. Okay. So, there is not exactly 1, but still right there will be some cases which will like so there is like 2 to the power of n minus 1 minus 2 to the power of k minus 1. Okay. But the number of undetectable faults is 2 to the power of k minus r, and if you remember right, it was previously 2 to the power of k in the case of linear codes, okay, and that essentially gets significantly reduced. Okay. And that is why right people have tried to apply such kind of techniques and get interesting designs. Okay. So, now with this background right we can basically right see the design. So, here you can see that this is your cubic function which has been used, for example, this is the cubic function here used and here is the cubic function which has been used. But before that there is a compression and L compress. Okay. So, what are this? So, the L compress or the compressed right is as I have said just now. So, if you remember like in the mixed columns what we did basically, we basically found out the parity of every byte there, right, and the compress function is nothing but it basically kind of exhausts the parity of each of these columns. So, you saw that like it does not change for the mixed columns, okay, and therefore right you basically get a mixed column for I mean a parity for this column that is denoted as L0. Now, this is denoted as L1 and this is denoted as L2 and this is denoted as L3. So, totally right you have got like you have got a parity for 4 bits here, you have got a parity I mean for 1 byte here and so on, right. And therefore, if you basically take an XOR of all these things, right, and then you get L0. So, this total set is essentially what you get at the output of this compress function, okay, and that is followed by an L compress, and this L compress is nothing by a map. So, therefore, right, imagine that this is like say R bits, for example, you would like to compress this into RL where RL is less than R. So, therefore, you just kind of multiply this output by a matrix whose dimension is say R cross RL, okay. So, and then you get this result which is RL, and then you perform the usual cubic operation and then you basically check. So, this essentially together stands for something like your P as I just now denoted, okay, and likewise here. So, then you finally do a check and the idea and the results say that there is a significant improvement because of this, and this is essentially leveraged in some of the designs, okay. So, therefore, the idea is that the question is right, there are several detection techniques as we have seen, but the bigger question is right, does detection always guarantee security? Okay. So, here we will bring the idea of what is called as we will discuss with taking one of the redundancy techniques which is very popular, and that is the time redundancy countermeasure. So, as we have seen that here we do an original computation, we again redo it by a redundant computation and then we check. So, there can be two strategies which I can take if it is not equal. So, one of them could be that I suppress the output, but a more or better way would be to randomize the output. So, the attacker even does not know, right, because even if you suppress an output, that means the attacker knows that there has been a fault. Okay. In one sense, that is also an information leakage. So, a better strategy would be to randomize the output. Okay. But however, like for most part of our discussion, right, I will assume that the output has been suppressed, but it can be kind of extended to even for the case where the output has been randomized. Okay. So, what we do is that if there is a mismatch, then we basically suppress or randomize the output, but if there is a match, then we generate the output. Okay. So, then the reason, one of the reasons why we kind of show here as red here is that this is fine, because if you are suppressing an output, then the attacker does not get any information, but what we need to analyze is this situation where there is a match, right, and the attacker gives an output. So, now remember that this match is kind of assumed by the designer is that if there is a match, the designer is kind of assuming tacitly that there has been a no fault. But in reality, what can actually happen is that there are two faults and these two faults are cancelling each other. Okay. So, one can argue what would be the probability of such kind of fault collision. Okay. So, imagine that you have got two possible states, and you would like to calculate the probability of fault collision. That means, right, you would like to kind of calculate the probability of two identical faults in the original as well as in the redundant round. Okay. So, you can easily work that out. Imagine that suppose you have got possible faults denoted as say F1 to Fn. Suppose this is your all possible faults, and the probability of inducing each of the faults are suppose denoted as P1 to Pn. Okay. So, then we know that the probability that you basically inject the same fault in both occurrences can be found out by the sigma of pi square, because like it is basically like you are kind of like inducing the same fault. Suppose you are inducing the fault belonging to F1 in both the redundant as well as the correct operation, or the actual operation, that means in the original and the redundant round. That probability would be P1 square. Okay, likewise similarly for F2 this will be P2 square. So therefore if we add it up, right, you will get sigma into pi square. Okay. Now observe that the variance of the fault distribution also can be written as sigma of pi square by n. Suppose there are n possible faults, and this is equal to nothing but minus 1 by n whole square. Okay. So that means that sigma pi square can be easily calculated as n multiplied by the variance, okay, plus 1 by n. Okay. So therefore the probability of the collision, so let me write this as probability of collision, is n multiplied by the variance plus 1 by n. Okay. So now note that when the variance is 0, that means when you have a uniform fault distribution, then this probability would be equal to 1 by n. Okay. That means like suppose you have got if you consider the AES state matrix where there are like 2 to the power of 128 possible faults, right, then this probability is negligibly small. But at the same time one should be careful that if I observe a variance, that means if I kind of increase the bias in my fault distribution, which can be measured by this variance statistic, then I can actually increase the probability of collision significantly. Okay. So therefore if the variance increases, then the probability of collision also increases. Okay. And that essentially is something which is kind of stated over here as the non-uniform probability distribution of faults in the fault space will enhance the fault collision probability. Okay. So we would like to therefore take care of such kind of scenario. So therefore, right, if you take this into account, so therefore, right, this is the classical scenario where all faults are equally likely, then this probability, because the variance is 0, the probability of fault collision is equal to 1 by n, which can be small. However, right, what we can observe is that if you, so here is an example to show like that the variance is a measure of this biasness in the fault distribution. So imagine that you have got a fault model where all the faults, right, like F1 to F8 occurs with equal probability, then the variance is 0, whereas you can observe that this is more biased fault injection, whereas this is even more because there are certain faults which never occur, then the bias and the variance increases further. Okay. So therefore variance is a useful measurement for the degree of bias in the fault model. And as we have observed, right, then the probability of fault F1 equal to F2 is directly proportional to the variance. So therefore if the variance increases, this probability of collision also increases. So what is the adversarial perspective of this? So you have got a precise fault model versus a biased fault model, okay, and the question is, right, whether you can exploit this. Okay. So this brings us like to what is called as fault intensity, and gradually we will define what is called as differential fault intensity. So this is based on a work which was published in FDTC in 2014, which defined what is called as fault intensity. The idea is that if you take a say let us consider a combinational logic which has got a 4 input and 4 bits output, and then gradually we start to increase the clock glitch. That means we try to kind of increase the like try to induce a fault by like a clock glitch, for example. Similarly I can do it for maybe other mechanisms like voltage glitch and so on, but let us consider a clock glitch here, and you can see that the fault which you observe in the output, right, is not really random. Okay, which we have been assuming in the context of differential fault attacks. So what is shown here is that if you are increasing the clock frequency, for example, the first line which fails, right, is the critical, which is in the critical path. That means you just got the maximum latency. If you increase it further, right, it is most likely that the next one will fail. Okay, and therefore, right, even if you repeat this pattern, you would expect a probably like a probably repeatable pattern. Okay. And more importantly, using the clock injection frequency, you can actually control the number of bits which are getting affected. Okay. For example, right, if after I have done a bit of characterization, I can like probably inject the clock frequency or operate it in a situation where I get like faults which are like this, which is like a single bit faults, for example, or maybe like faults which has got 2 bits maximum, which get corrupted. That means, right, I am trying to kind of induce faults which are biased and not really random, and that is a very important thing, because like when we talk about classical fault tolerance, then we basically assume that all faults are equally probable, because like in nature largely the faults are kind of unbiased. But when we talk about fault attacks or fault tolerance in the context of cryptography, one thing which we have to keep in mind is that the adversary can accordingly manipulate the fault injection and hence can bias the fault injection. Okay? And therefore, we have to kind of revisit the fault tolerance techniques, keeping this kind of biased nature in the fault distributions. So therefore, right, this brings us to what is called as differential fault intensity attack. It basically combines fault injection and the principles of differential power attacks, or as we have seen, or in general side channel attacks. It basically induces biased faults by varying the fault intensity. It applies a hypothesis test with biased faults and uses biased faults as a source of leakage. Okay. So let us see how it works. So there are two steps in this particular attack. In the first step, right, you basically do a fault injection which is biased. So this would probably happen more, right, in case of when you have got a low cost fault injection technique, so like voltage glitch or clock glitch, or even in case of maybe an EM injection. You will see that which is not very controlled well. So you will see that, for example, you will have got F1 to FQ, all these are different fault intensities, right, and when you are injecting the fault, what is happening is that the state is getting corrupted, and therefore you are getting, say, Q such injections, and all of these injections have got, like apparently a biased nature in the faults. That means probably you are getting, like a fault here which is, like maybe a 1-bit corruption or 2-bit corruption, but it is not random. That means all faults are not occurring here with equal probability. Okay. So therefore you get correspondingly faulty ciphertexts. Note that this attack, right, is very kind of significantly different from the classical DFA in this aspect. In classical DFA, we basically do an attack where we have got the faulty ciphertext and we also have the correct ciphertext. But here this attack works only on the faulty ciphertext. Okay, so imagine that I've got like C1 to Q, and all of them are faulty, and therefore they are denoted as C1 dash to CQ dash. Okay. So now there is a step 2 of this attack. In the step 2 of this attack, we do a hypothesis testing with biased faults. So what we do here is that, so this extraction is something like that of a side channel attack or side channel analysis. So you basically guess the correct key, and it helps in observing the bias in the fault distribution. Okay. So the idea is that if you are able to correctly guess this key, then when you kind of invert back, that means you exert the ciphertext and you take the inverse S box and you come to the location or the site of the fault injection. Remember, here was the site of the fault injection at the input of this S box. You should be able to see this bias. Okay. And if you are basically making a wrong guess, then you will not see this bias. You will basically see a random distribution. Okay. So so basically for that you need a distinguisher, as we used in the context of DPA. So one of the very common forms of distinguishers which is used here is this, that is you basically guess the key, that is as shown here as K tilde. You take the faulty ciphertext, you apply the S box inverse and you find out this S tilde. Okay, and then you accumulate all of them, and then you basically take the sigma of the Hamming distances of this. Okay. The idea would be that this Hamming distance, right, you are basically assuming that you are operating in a region where this Hamming distance is small. Okay. So therefore you would assume that this sigma like that should be minimized when you are correctly guessing the key. That means for the correct guess of the key, this particular parameter sigma of the Hamming distance of S tilde should be minimized. Okay. So therefore you can again, like applying a similar to what we have done in the DOM or the correlation attacks, you can basically kind of arrange the keys or rank the keys with respect to which basically minimizes this parameter. Okay. And the one which minimizes most, or which gives the minimal output, is the candidate key. Okay. So likewise, right, we'll see how we basically experimentally verify it. So we basically kind of consider two situations. In situation 1, we will assume that the attacker has got no control on the target byte, and in the situation 2, we will assume that the attacker has got, or in the first situation, the attacker has got control over the target byte. In the situation 2, the attacker has got no control over the target byte. Okay. So now what we observe here is that we basically considered like different kinds of fault models. So for example, the fault model can be a single bit upset, it can be a single byte double bit upset, it can be a single byte triple bit upset, it can be a single byte quadruple bit upset, and there can be other kind of byte faults also possible. Okay. In particular, let us consider about the SBU, or which is the single bit upset fault model. Okay. So of course you can understand that if I've got a fault model which is more precise, then it is also more costly to achieve. Okay. So now we basically, again, as I said, that we basically kind of characterize our device, and we see that in situation 1, where we assume that the attacker has no control, has got control over the target byte, I need lesser fault injections to get my required faults. Okay, whereas in the situation 2, where I am basically more haphazard in my fault induction, I require more faults, but at the same time, right, this is pretty manageable, and within these faults, right, I am able to create such kind of fault injections. Okay. So now what we will basically consider this and see how it kind of helps us to do the attack. So this is the hardware that we will be considering. Again, remember, this is just a recapitulation of our old design. This is an iterative architecture. We again use an like an arbitrary function generator to inject the first clock, and then we basically use the ChipScope Pro to basically monitor the internal faults. Okay. So then we basically do the same attack. So remember that we basically pre-characterize the device. We kind of know that if the device is in this particular frequency range or operated in this particular frequency range, then with more probability we get faults which are of the single bit upset nature. Okay. And likewise, there are other fault characterizations also shown here in this table. And then we basically target that this particular implementation in both the original and the redundant rounds. Remember, there is a time redundancy which has been implemented. So now we basically kind of inject a fault in both situations, and but whenever we are injecting, right, we are basically ensuring that the operating clock is in this region of say 125.3 to 125.4 megahertz. So you can see that I am trying to operate in a region which I know that is more probable to create single bit upsets. Okay. And then basically I start guessing the key, and as I said that I would like to minimize the Hamming distance, or I can also use another alternative parameter which is called as a squared Euclidean imbalance. So I would try to kind of maximize this parameter, because you can see that like if the guess is random, then this would be something like 1 by 256, and therefore this would be pretty much going to 0. Okay. But on the other hand, right, if my guess is correct, then this I will get a like a non-zero value here, and if I add up all those non-zero squares, right, then I should get a larger value. So therefore in this case the correct key would minimize this parameter of hk, but in this case the correct key would kind of maximize the parameter sk. So you can actually use both the metrics or both the distinguishers together just to increase your confidence. Okay. So then what we observe here is that we kind of do a simulation. So in the simulation, right, we are basically assuming that an identical fault has been introduced into both the original and the redundant round. This is not an actual hardware, and we observe that typically these are the number of faults that you require to get the AES key extracted. Okay. So you can see that the number of faults here is much more than in the classical DFA, but you can assume that here there are certain advantages which we didn't have in the case of DFA. Okay. So likewise, right, you can actually we also did like a simulation 2 where like we are basically varying the degree of bias by like controlling the variance, and then right we basically plot them, and here are some plots to observe. Here you can see that if I increase the number of variants in both the cases, right, whether it's a scenario 1 or scenario 2 where you have got perfect control on the byte fault or you don't have perfect control on the byte fault, in both the cases the number of faults is reducing, because as we discussed, right, that if you increase the variance, then the probability of successfully defeating this countermeasure is more, and therefore you need lesser and lesser number of observations. In fact, right, you can observe this also on validate this on actual data. So this particular column shows that what happens when you actually do it on a real life implementation with fault countermeasure using time redundancy, and you can see that the observations match pretty much with your theoretical simulations. So therefore, right, I mean the comments, just to conclude, right, some of the comments would be that the bias of a fault model can be quantified in terms of the variance of the fault probability distribution, and detection based countermeasures are vulnerable against biased fault attacks that are practically achievable. So the question is, right, what you really want to do? You basically want to cover all of the essential, what we do in classical fault tolerance, or you want to really cover almost all. So therefore, in a classical fault tolerance, we basically do almost all. That is, we kind of try to pretty much cover almost all, but what may happen is that what we probably need to do here is that we probably need to cover all of the essential, because like in cryptography or security, right, even if there is a small window of like of an attack, and the attacker can actually exploit that window and can like collapse the entire security of your system. So to summarize, we have discussed about DFA in the previous classes, where we basically induce a fault, observe the difference of the correct and faulty pairs, derive equations to obtain the key. On the other hand, what we discussed in today's class is what is called as DFIA, or differential fault intensity attack. So, here we obtain non-uniform faults or bias faults. You can see that it is a difference from the DFA, where we assume random faults, okay, through non-expensive techniques, and then we perform side chain analysis like power analysis to exploit the bias. Okay. So, to conclude, detection based schemes are a popular strategy to prevent fault attacks. CED schemes or concurrent data direction schemes are efficient fault tolerance strategy. Parity based schemes are useful for making AES like crypto systems resistant against fault attacks, and time redundancy countermeasures are vulnerable to DFIA. So, we still need to kind of figure out what to do, and the references that we have followed here for this part is shown here, and thank you for your attention.